Hello everyone. In this video I want to show you something nice and exciting. A projectile motion with air drag added, but we try to make this air drag quite a bit realistic. One of the projects I give in my dynamics class is to simulate the motion of a projectile subjected to air drag, no airlift, we neglect that, and any wind or anything. So the only forces are drag and the gravity. And for simplicity in that class, I asked the students to use the formula that we know for drag, half of drag coefficient CD times density of the air times cross-section A, which is pi r squared times velocity squared. Now this formula is not simplified. The simplification is in CD and rho of air. So in the class, typically I ask the students to use a constant number for CD and a constant number for rho of air. So like I asked them to use 1.225 kilogram per meter cubed for rho of air, which is at 0 elevation from the sea and at a temperature of 0 degrees Celsius. And for drag coefficient, I asked them to use 0.5. Okay, so I asked them to make life easy. I give them a material. I say, let's say it's a ball made of steel with this much of density and the radius of it is 2 centimeters. So from here, from this r, they can calculate the cross-section, right, which is pi r squared. And the mass, of course, that you need in your governing equations, mass is rho times v, and v for a sphere is 4 pi over 3r cubed. So they can calculate mass from here and then plug it into the governing equation. Now, if you look at the governing equations in the x direction, you have the cosine component of the drag force in the negative direction. In the y direction, you have both gravity and the sine component of drag both in the negative direction. So these are your governing equations. Of course, they are highly nonlinear, and you need 4 initial conditions, which I'm going to talk about it. But the v that we have in this fd, right, which you can see, it's square root of x dot squared plus y dot squared, right? And theta, the angle of the projectile with x-axis, is tangent inverse of y dot over x dot. Okay, so if you plug them into these equations, your equations are going to be coupled and they're going to be nonlinear, second order both, and they have to be solved simultaneously. I mean, you can simplify the cosine of arctangent of an angle, and if you do that, this is basically going to be like CD over 2 rho of air, right, times A. And then instead of the V squared cosine of theta, so one of those V and cosine of theta, you make it Vx. So it's going to be V times Vx, which is like this. Okay, so it is going to be like, still, you see that clearly in the x double dot equation there is y dot, and in the y double dot equation there is x dot, right? And clearly your equations are coupled, nonlinear. You have to solve them numerically, and there is no way around it. Okay, so again, if you plug in and simplify sine and cosine of arctangent, you'll get these 2 formulas. Okay, but that's it. So now this is what my students do in dynamics class. Now here I want to raise the bar one more time and talk about that the drag coefficient, which is not really constant, and the density of air, which is not really constant. So here we try to model the coefficient of drag and the density of the air as a function of velocity and elevation. And from there, then we can make it more realistic. So how do we do that? Here, we assume for now that the air is an ideal gas model. Okay, you know air is not an ideal gas model, but here we do simplification. We can make this model more complicated. And here we also assume that the temperature at elevation h drops linearly with elevation. So if at the sea elevation the temperature is 288.16 Kelvin, right? As you go up, the temperature linearly drops. Now, in reality, even it's not accurate. It's not super accurate. It's not super linear. But here we assume that the elevation is not significantly increasing, and the projectile, you'll see I'm gonna simulate, does not go up more than like 500 meters or so. So here we do this approximation for temperature. Why do we need temperature? Because we need it for density. The density of the air depends on the temperature, and temperature depends on the altitude. So we use this formula here to estimate the density of the air at elevation h compared to the zero elevation rho naught, which is this number here. And the constant of drop in the temperature is this number, this alpha, which is so many kelvins per meter of elevation. And you need this exponent of ideal gas here, 5.2561. So from here, once you have rho naught, T naught, you plug H into this top equation to get T of H and plug it down here, you should be able to calculate the density at elevation H. So rho is not constant rho of air. It is actually what? It is a function of the elevation. Or in this case, you might call it y instead of h. That's the same thing. Okay, so this is more realistic. Again, there are limitations in how the temperature is changing versus elevation, and whether we are going with an ideal gas model or not. We can make these even more realistic by changing these two assumptions. But again, once you learn how to do it this way, you can make it more complicated. Now, for rho, it's easy. You have a formula. The hard part is the drag coefficient. For drag coefficient, which is a function of velocity or Reynolds number for a sphere, a ball, is defined as its density, the density of the air, times the velocity of the ball, times diameter of the ball, right? So this is 2 times r. That's rho is the same rho here, and mu is the kinematic viscosity. At the zero elevation, it's this number for the air, but in general, even that mu is not constant. That does depend on the temperature. And again, here is a simplified rule. We assume that viscosity is proportional to the square root of the temperature in Kelvin. Okay, again, these are not ideal and perfect, but that's the matter of fact. So Reynolds number itself is a function of velocity and elevation, and that will determine the drag coefficient, CD. You see there are two curves, one for a smooth ball, one for a rough ball. Here we go with the smooth one. And you see there is no formula. These are all experimental data. So we're going to use this dark green curve. And how do we get these numbers? Well, here I did that hard part for you. I used the G input command in MATLAB. I uploaded this image into MATLAB. I clicked on a ton of points and then converted all of those points into actual data. And here in my Simulink model, if you double click, I have provided those data for you called XNN and YNN. Okay, if you don't like them, call them whatever you want. Okay, so these are my X data, these are my Y data, or these are the CD values, these are what? The Reynolds number values to form that graph. And then, so here we have to do a lookup and interpolation. So I approximated this at a ton of points. I clicked on a ton of points here between 10 to the 2 to 10 to the 7. I used a ton of points on this graph, and then what? As I said, now if you give me any specific Reynolds number, let's say here, I do an interpolation of the two numbers next to it, a linear interpolation. Okay, and that way I can find you a good approximation of the drag coefficient, which you see here changes anywhere from like 0.2 all the way to 1. Okay, so your drag coefficient is not really 0.5. It changes. It changes based on the velocity and based on the elevation. So it's a complicated function, and it's a lookup table really. So how did I do it? Look here again. So this is my Simulink model, right? This is the x double dot. I double integrated it to get x dot and x. Y double dot, double integrated it to get y dot and y, and send them to oscilloscopes as well as workspace. I stop my simulation when y becomes less than 0. So when it hits the ground, I stop it. Here I take x dot and y dot and pass them to arctangent 2 to get me angle theta, so I can use sine and cosine of it. I square x dot and y dot, add them together to get v squared. I also use the square root of that, which is v. I pass that v along with y, or h in our simulation, and the rho, the density. I pass all of them to calculate what? To calculate the Reynolds number. V rho d over mu, where d is 2 times radius. Okay, and you see here, I calculate my temperature using the same formula I just showed you, right? That linear drop. I calculate my temperature because I need my temperature for viscosity. And then I calculate my viscosity here, proportional to square root of t, such that at t naught, the value is mu naught. This is mu naught and this is t naught. Okay, so I use this square root function to calculate mu. Now I get v from input, and rho is calculated in another function, which I show you, times d over this mu that I calculated inside here. That gives me a Reynolds number. I pass it to the function interpolation 1. And with all the data I get from that graph, I can calculate CD and send it out. And look, this is the other function I have, where you calculate the temperature and use the formula I showed you to calculate what? The density, this guy here. Okay, so I have everything. And this fixed portion of the drag formula, 0.5 times a, is multiplied by v squared, then multiplied by the drag coefficient, then multiplied by rho to get you the drag force. And then that drag force is multiplied by sine of it and by cosine of it to go into the equations for x double dot and y double dot. They are divided by m. The sum of the forces divided by m. Both of these gains are 1 over m. And this is my fixed mg term. And this is the MATLAB file that runs the Simulink. So all of the parameters I need to have are specified here. The initial condition is 200 meters per second launch velocity, and the angle of launch is 45 degrees. All of these initial condition will go into Simulink, into these blocks, into these integrators, okay? If you look at inside these integrators, you see x dot 0, y dot 0, right? Which are v naught cosine theta and v naught sine theta, and this is x0 and y0. Here I go with 0 and 0, so I launch it from the ground. And then I run my Simulink. I get the x and y data from those oscilloscopes, and then I do an animation. So let me show you this. And you see that when air drag is present, the projectile motion is not going to be a symmetric parabola, okay? It's going to be a skewed parabola, and it is going to go far less than what you can imagine. Okay, so you see here that it is going up to about 440 meters or so, and the range is a little bit over 1100 meters, right? Well, if we want to use the theoretical formulas that we had, the climax point, right, y max, if you remember, it is a v naught squared sine squared of theta divided by 2g. In this case, my v is 200, so this guy is going to be like 40,000. This guy is 1/2 because it's 45 degrees, and this is roughly 20. So you should get about 1,000 meters high. Your projectile should go about 1,000 meters high, and the range, if you remember, it is v naught squared sine of 2 theta divided by g, and this is 1, this is about 10, and this is again 40,000. So it should go to about 4,000 meters. So it should go forward 4,000 meters and up 1,000 meters, but you see it does far less than that. The range is about a little bit less, more than 25% of what we predicted, and the height is about 43% of what we predicted. And you see, it's absolutely not symmetric. Okay, so this is a lot more realistic projectile motion compared to what we do in a simple physics class, and we have these fancy formulas. None of them will work. We have to model everything. And again, here, this is not super realistic compared to what happens in real life, because this T function is not exactly this. The rho is not exactly that because it's not an ideal gas model. And this drag coefficient is not too bad actually, but remember, I just approximated it by a bunch of points. And this viscosity is not also a perfect function of square root of T. So here we did a lot more realistic than what you normally do, but again, compared to real life, this is not 100% realistic, but of course, clearly a lot better than, again, what you do in a physics class. So I'm going to upload both this MATLAB file and the Simulink file for you, and feel free to use it, play with it, and see for yourself a more realistic projectile motion. Okay, if you ever decide to do a jumping with motorcycle, doing stunts or something, make sure you do your simulation with this one, not those fancy formulas, and assume that you're gonna land 4,000 meters from where you jumped. No, you probably will not even go more than 1,000 meters. Okay, so be very careful about it. Hopefully this video was useful to you. I'll see you in the next lecture. Thank you.